Dr. Sen, you're muted.
Okay, so people ask me about how to do linear approximations. What's the meaning of it? So basically, you're locally replacing some function by something linear. So you replace something difficult by something easy, so you can do all the computation. The trade-off is you're not that accurate anymore. Okay, but the good news is if you're close enough, then you won't be too much off. The same idea applies in 3 dimension. Hopefully my code is still working. Okay, this is a, can you guys see it? A master Yuda graph. Actually, yeah, okay, it's working. So basically, if you look at this graphics, right, what you're doing is Yuda is smooth. Do you agree? Like his skin, his everything is just smooth. Okay, but locally, if you zoom in, now I'm really hesitant to do that because it may freeze my computer. But either way, if you zoom in, I think you can kind of get the idea. That is, every single piece of his skin and his clothes and everything is replaced by a flat, linear plane in 3D. Okay, so that's the power of linear approximation. There's no way you can do anything smooth, but you can replace it locally by something flat. And if you have enough polygons here, actually the whole thing, from what we can tell, will be as smooth as, you know, the resolution our eyes can take. That's the beauty of linear approximation. And this is how actually everything in computer graphics has been done. You can look at Frozen, for example, Disney movies, DreamWorks movies, and you can look at video gaming with all the smooth skins and water and everything. Everything is actually approximated with something linear. Because once you have that, you don't have to actually draw all the pictures. You just take something linear and you do a linear transformation. You can make that thing rotate. You can make that thing, you know, shift, scale, without having to redo all the data points. So that's the beauty of linear approximation. And this is probably the ultimate application for now, which looks pretty nice. By the way, if you take linear algebra, this will be, if you take mine, this will be your first homework to make Yuda rotate in the way I want. You can make him flip, no, upside down. You can make him rotate horizontally. So that's the idea of linear approximation. Now I got a question from the project 4. Since many people are asking that, why don't we just go over it? It's a nice application of calculus. Okay. So basically what you're trying to do is you got a guy, and he's doing surgery. He has red blood cells. Out of his 5-liter blood, he roughly have 45% red blood cell. Okay. So now what's gonna happen is when this guy takes a surgery, he's gonna bleed. So he's gonna lose blood. Of course, he also lose red blood cell. 45% just got lost. Still okay? Meanwhile, you're actually adding artificial blood to him, but that artificial blood does not contain any red blood cell. Okay, so in this way, you actually bleed. Meanwhile, you're actually injecting blood to him, so he maintains a constant blood volume, which is 5 liter. But gradually, the red blood cell got replaced because you bleed out red blood cell. The thing you add in does not have red blood cell. Make sense so far? Okay, so number 1, how do you model this? Well, differential equation. Let Y be the blood cell volume. So clearly Y is changing. What's the changing rate of the blood cell? Well, at every moment, my blood cell is lost due to my bleeding. How fast are you bleeding? You bleed 2.5 liter in 4 hours. This is how fast I am bleeding. 2.5 divided by 4. Sounds good? Times what? Times the concentration, because when you blood, part of it is just regular blood, part of it is RBC. Okay, so times the concentration of the RBC. Okay, what's the concentration of RBC? It cannot be 45% anymore. At first, it's 45%. As you add more and more artificial blood, the whole thing actually got diluted. Make sense so far? Okay, so basically, how do you calculate concentration? That is going to be my current red blood cell, which is my Y. It may be big, it may be small, divided by my total volume of blood, which is always 5 liter. Adam?
Yeah, so the question I had is that 2.5 liters, isn't that also diluted because you've been adding saline solution as you're bleeding out? So the blood that you lost at the end isn't just purely blood?
Beautiful, yeah, that makes sense. But hey, what I got here, this is going to be the speed I lost blood, including the liquid plus the RBC.
Okay.
Times the concentration of the RBC. So I only consider the RBC here. That is because I times the concentration.
Okay.
If I don't times the concentration, then of course what you're saying was a really big concern.
Okay.
Yeah.
Sweet. Thank you.
And of course you have a negative here because it's losing. So let me say rate of blood loss, but only part of it is RBC, which means we times the concentration. And the concentration is changing with respect to time. Okay. Is everything making sense so far? All right, now we just have something we can simplify a little bit, cancel all the terms. This is basically the differential equation. Now, do you know a function which you take the derivative equals itself times a number? That is y equals c times e to the negative 1/2 t. Okay. That will be the final answer, which solves this process. That's where we got exponential decay. Okay. If that is good, the only thing is missing is, what is this constant? Well, you do have one more condition, that is at the beginning. What do you have? You have 5 liter times 45%. That is your initial RBC. It's almost the same as, when you do the compound interest, the initial deposit, right? So finally, the solution for the first one is going to be this times e to the this. And this models your RBC volume across time. So question for number one, answer for number one will be this. Sounds good? All right. Number two. Now what are you going to do? Well, if you keep this process without doing anything, you lose blood cell, which is really hard to recover. Okay. Now what they do are the following. When you're trying to do this, you lose blood because you have a certain concentration. Okay. What I'm going to do now is, at first, I'm going to extract part of your blood and just keep it here. And then you go ahead and do the surgery, you lose blood, whatever. Still okay? And when you finish the surgery, I just add this one back. So it's almost like I take part of your blood cell out, let you go and bleed. When you finish, I put this cell back. Okay, that's what we're trying to do. Okay, this process is called ANH. Very easy to understand. Now the problem is, how much do you want to take out? Well, the best case, you take all the blood cell out. You do the surgery. Okay, then you put all the blood cell back. You don't lose any blood cell. The problem with that is then the human will die before you even do the surgery because all your blood cell is gone. Okay, so they did put a threshold. You can keep taking things from human, but the concentration cannot drop lower than this. Sounds good? Okay, that means, yeah, you can, by extracting the volume, you can definitely take this out, but the amount you take out cannot exceed certain amount such that the whole thing drops to be 25%. Otherwise, the human dies. Okay, so what is 25% of 5 liter? That's 1.25 liter of RBC. So you take this much out with a certain concentration, 45%. This one should be your initial 2.25 minus this one. Then how much is the volume? It's very easy to calculate. is going to be 1 divided by 45%. Okay, that's how much liter you can take out of the human blood, such that the final thing does not drop below this. If you take a little bit more, you won't have 1.25 anymore. You drop below 25%, the human just dies right away. Okay, not even, you're basically using a surgery, just doing a surgery on a corpse. Is number 2 clear? All right, so number 3. Basically calculate the loss of RBC for twice. Okay, step 1, when you don't do ANH, how much blood, red blood cell do you lose? Number 2, with ANH, how much blood cell do you lose? We're hoping for when you add in ANH, you lose less. Okay. Otherwise, you're not saving people, you're hurting people. Sounds good? Okay, so let's compare the 2 situations. First, without. We already know it. Your blood cell is like this. Okay, so at the first, you have 2.25. In the end, which means after 4 hours of bleeding, your blood cell is like this. So how much did you lose? Well, you just take the starting minus the ending. You got something roughly like 0.89 liter. So you lose this much red blood cell if you do it without ANH. Okay. Now with ANH, okay, you need to redo what we just did. You find, well, number 1, the process is still like this. So nothing changed. However, your initial value is not 2.25 anymore because you took all the blood out, leaving him only 1.25 of liter of RBC to start with. So same process, but this time we start with fewer RBC because we saved some of them. Okay, then T equals 0. This much. T equals 4. This much. How much did I lose? Well, use a calculator. It's roughly, I think, 0.49. Compare these two, you can see, okay, applying ANH, you basically saved 0.4 liter of RBC loss just by extracting them before the surgery. Almost half of them. Makes sense to everybody? Okay. So basically, what did you change? You are losing the blood cell at a certain rate, right? What you did was you lowered the concentration. So for the same amount of bleeding, you lose fewer RBC because your concentration is lower when you're in the full capacity of RBC. So as time goes by, you accumulate all the loss, it's definitely going to be fewer. Okay, that's everything we have for product 3, roughly. Any questions so far? So it's pretty nice, isn't it? Like a lot of procedure and treatment are actually calculated using this way. I know in class we do a lot of complicated derivatives, you know, log differentiation, whatever, but actually you will be surprised whenever you go ahead and try to apply calculus in real life. Most of the cases, you just have very simple ones, Okay, as simple as this. It won't be too difficult. The idea is more important. Okay. If you're from Chem major, this is actually very similar to what you do when you add solutions. 25% solutions, and maybe you have a 75% solution to start with, and then you just keep draining while adding. So eventually, how the concentration is going to change. This is actually a very common process you see in chemistry. Okay, sometimes you got lucky, you add in 5 liter, you drain 5 liter at the same time, so the total volume doesn't change. But sometimes you actually add more, okay, and then you drain less, or maybe drain more. So the total volume is also going to change. You will be surprised, actually, just by cleverly design this process, you can save your solutions. Let's say you want to prepare 20 liter of something with 50% concentration. Sounds good. And you start with something with 25%, you have unlimited supply of them, and you start with maybe, I don't know, 10 liter of 75%. So you're going to go over this process, but by designing them cleverly, you can actually see you use different amount of 25% solutions. Okay. There will be a best way to actually only use 3 liter to make the solute you want, compared to you use 13 liter to make the solute you want with the same concentration. So yeah, there are some clever design there. And for biology, I mean, clearly this is blood, brain fluid, or whatever. You always have a threshold you need to meet to make people safe. And, that is nice. Any other questions regarding the project or homework? Adam?
Yeah, could you go over homework 4.1, problem 11?
All right. For a problem like this, we can see the procedure is pretty standard. Find extreme values. 3 steps. Okay. Yes. Critical points and ending points. So we do have the interval 0 to pi over 2. We got 2 ending points. Clearly, this one does not have a solution. To make it does not exist. We do have possibilities such that this one is 0. That is where usually a lot of people get stuck. And there's no shortcut. You need to go back to pre-calculus and try to remember that when you see things like that, you need to use half-angle formula. But once you know that, the rest will be easy. Clean things a little bit. Positive 2 sine square x plus sine x minus 1 equals 0. Draw the unit circle. -1 is here. 1/2 is here and here. You are only looking for 0 to 2 pi over 2. So the only solution out of this will be x equals pi over 6. So 3 points, pi over 6, 0, and pi over 2. The rest is just doing the computation. 2 cosine 0. Zero, zero. So this is the minimum. The maximum depends on how big this is. This is going to be square root of 9 over 4, 3, which is square root of 27 over 4. This is going to be square root of 4. Which one's bigger? Clearly this one's bigger. So max. Final answer. All right, so Weber takes it. I think the key part is solving this. Sounds good? Okay. How quick can you reflect on double angle formula depends on how solid your training in pre-calculus is. That's why I say sometimes memorizing the formula is way better than just having it on a formula sheet, because you never know when you need a sheet. Okay. Aaron, do you have a question regarding this or something else? Okay. Then
No,
let's wait. Okay, Justin, what do you have?
3.10, number 5.
I think we did this, or did we? Let's see. Find dy of Did we do it in class? This one? Okay then. So basically, if you're looking for dy, you actually you know dy over dx, which is f prime x. So dy is nothing but times dx. That's the idea of differential. Okay. Now, if you're looking for dy when x is 1/3, dx equals -0.1, then you basically just plug in. Oh, positive. Okay, you have a pi. This. That will be the answer for the second one. So once you have the differential calculated, formula written down, you just plug in the corresponding change. Okay. All right. Aaron?
3.10 number 2 and 4.1 number 7.
Find the linearization of this one at 4. Okay. 3.2 is pretty standard. So I will just quickly do it. And you try to see where you get things wrong. Linearization at pi over 6. So basically we have the tangent line. Point pi over 6 sine pi, which is 0. Slope so that will be it. I think your question here is you missed a 6 by channel. Okay. Now 4.1 number 7. Ho, 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 ho. Critical points of so I guess there's no tricky part here. Just do the derivative. Okay. They're both nice, so it will never be does not exist. Probably the only critical points will be this equals 0. Let's factor everything out. You have x equal to 0 is possible. X equals negative 13 over 8 is possible. And this part can never be 0, so doesn't matter. Final answer, this and that, coming from here and here. All right. Okay, Emma. I didn't hear you. Did you? 3.10 number 6. Linear approximation. Okay, linear approximation. We know nothing about this. Clearly, we'll know everything about E at 0. And the 0.005 is not too far. Okay, so I will find the linearization. at 0, which give me 0, 1. F prime x is this, so f prime 0 is 1. Together, that will be the linearization. Okay, keep going. Y equals 1 plus x. Now instead of plugging negative 0.05 to the original function, I'm plugging it here, which give me that will be my linear approximation. Sounds good. The real one, if you use a calculator, okay, from here we can see, well, we did a pretty decent job. Okay, the error is really small. All right, anything else? Back to 4.3. We basically did a lot of stuff. Okay, now let's just go back and try to list them all together and then talk about how to use it to draw the graph of a function. Okay, so let's take a quick review. We basically were talking about how much information can you get from f prime x. Okay, and we'll basically say two informations. Number one, increasing, decreasing. Increasing. The way we do it is actually we find where 0 and determine, okay, positive, maybe negative, maybe positive, whatever. Then we roughly know it's going up or down on each interval. Once we have that, we have some additional information. That is, well, if it's going from positive to negative, we kind of have a local maximum. If it goes from negative to positive, okay, we kind of have a local minimum. Okay. If it's positive, positive, negative, negative, that means we have something like this, something like that. We call it a saddle point. Okay, that's all the info we got from first derivative. Increasing, decreasing, and the side product, maximum and minimum, or saddle point. Then we're not happy. Why? Because increasing, decreasing give you something that like this. We really want it to be, increasing like which way to make it smooth. So we have something called concaving up and down, which is related to second derivative. Concave down. Okay. Then, of course, when f prime prime x change from positive to negative, negative to positive, we call them inflection point. Okay. Finally, we have something called second derivative test. It's very simple. If f prime c equals 0, we've checked further. If the second derivative is bigger than 0, means concaving up, we have a local max. Less than 0, concaving down, we have a local max. Okay. It does the same thing we do here. Then we say, well, for our class, this is faster. So we stick with the top one. The bottom one become handy when you go into 3-dimensional. For example, like my mic. You can see there is clearly a local maximum here, right? How do you tell all around that this one is the maximum? You need to use the second derivative test in 3-dimensional. Okay. That's basically what we have here. Sounds good. Now let's use this information to draw the graph. Example, use the info from f prime x and f prime prime x to draw y equals so basically, we're just repeating the table we just created. We have a list of 4 things. And we say the last thing is not important, so we just do the first 3. First derivative okay? 0 here and here. So naturally 3 parts. On each part, we determine positive or negative, positive or negative, positive or negative, as we said before. You have all kinds of ways. Picking a test number, for example. Either way, you will figure out it's positive, negative, positive. Good so far. With that, time to draw. Local max here. Local minimum here. Sounds good? All the information from the first derivative, done. Now let's move on to the second derivative. Zero. Bigger than 1, positive. Less than 1, negative. But keep in mind, this is talking about f prime prime x. So positive is not increasing anymore. Positive means concaving up. Negative means concaving down. Okay. Moreover, inflection point at here. Oh. Everything makes sense so far? Finally, use that information to update the graph we just had at 1. On the left, you should have something concaving down. On the right, you should have something concaving up. Of course, I make it pretty. So let's see if I can do this. Yeah. The inflection point here. Does everything make sense here? Okay, Nick?
So just one more time, what is the inflection point exactly again?
It changed from concaving down to concaving up and concaving up to concaving down. So that's where your second derivative change sign. Okay, it looks like this. Concaving down, concaving up. So that's where the whole thing changed. Or concaving up, then concaving down. That's where the point change.
Thank you.
Okay. To think even more, what does the inflection point or what does second derivative mean? It means acceleration. Makes sense so far? So it's almost like you can imagine a car is going to the east. The moment you start, let's say you're Superman or you're Spider-Man, you start to use your superpower to push the car to the opposite direction. Will the car stop right away? Not really, but that thing is going to start to decelerate. That's where inflection point is. Before you were accelerating, but at that point you change from accelerating to decelerating. Okay? It doesn't mean that your derivative is going to change right away. That means your velocity will change right away, going from east to the west. No. But for a while, okay, then your velocity is going to start to change. So that's where your acceleration starts to change. That's a way to understand it. So before, if I look at this, what am I trying to do? I'm trying to accelerate faster and faster and faster until here I got pushed back. So I start to decelerate until finally I cannot even go against that thing. I start to actually go back. Okay, that's what inflection point is. Adam?
So I just want to make sure I'm doing that first part right. For the first derivative, are you plugging the values into the first equation or into the derivative?
Okay, 3 things. For fx, if you're deciding it's positive or negative, basically you're trying to decide is it above or is it below, right? For f prime x, when you're deciding plus or minus, you're deciding is it increasing, is it decreasing? For second derivative, what you're trying to decide is actually, are you trying to do this or are you trying to do this? So it's the same procedure for different things. F prime, and f prime prime, they all mean different things. Now back to your question. What am I trying to do here? I'm trying to decide is the thing increasing or decreasing. So which one should you plug in? F prime. Okay. Another thing you can think about is where did you get the zeros? F prime. Then you should plug in this. It doesn't make sense to get zeros from one thing and plug in all the numbers to another thing. Okay, cool. Aaron?
So if you have that inflection point that had both positives, would that become a saddle point then?
We don't have that. Actually, you have something concaving down and keep concaving down. So for that thing, we don't differentiate that. You notice actually we didn't even differentiate between these two kind of inflection points, right? There's no like maximum minimum. So it won't be called a saddle point because the shape won't look like a saddle. But that's a valid point. All right, that's all the info we can get from the first and the second derivative. We stop here. Can you go and get the information from the third derivative? Yes, but nobody cares. Why? Because the third derivative is called jerk. I'm not kidding. Like basically, you know, you have velocity, you have acceleration. What's the third derivative? It's called jerk. So we don't care about it usually. And do you have other informations you can add in? For example, how do you know it's like this, not this? Right? So from here, you can see you can add all the informations like x, y intercepts. You can add in the vertical asymptote, horizontal asymptote. You can add all those kind of things. It's additional. You don't get them from the first and second derivative. So later, if you want to make this pretty, you can keep adding the pieces you want to add, some old pieces you had before. But for now, we only care about the new thing, like the first and second derivative. So you can stop here. Okay, technically, you should go ahead and try to figure out the y asymptote, x asymptote, y intercept, x intercept. You should go ahead and try to find if there is any asymptotes. Okay, we just saved the trouble here. All right, does it work? Well, let's try to type it in. We have, where is it? Okay, we have y equal x cubed minus 3x squared minus 9x minus 2. Okay, let's make it prettier. Okay, what did we do at first? We calculate the first derivative and set it to be 0. We find -1 and 3. So we have 3 intervals. On the left, it was increasing. In the middle, it was decreasing. On the right, it was increasing again, exactly as what we did in our procedure. After that, we erase them. We get the second derivative and find at this point, on the left, it's concaving down. On the right, it's concaving up. Okay, with all the information, finally, we draw something which looks like this. Meanwhile, we get the inflection point, the local max and local minimum. Is everything clear? That's basically what the whole procedure is. Okay. I would say nothing difficult, rather than you probably just want to practice 2 more examples and then you're all set. Okay. We don't have much time in class left, so I will leave that part to you to do the homeworks. You have plenty of examples for you to asking you to do this and bring them to class if needed. So no more examples in class on this section, unless you bring in some.